Okay, welcome back. This is the second presentation of mine, which is a deep dive into our best-in-class real-time database solution, Firestore. It's a last-minute change. I know we're supposed to have a different presentation. However, due to unforeseen circumstances, we'll have this one instead. I really hope you enjoy it, and I think it gives a lot of business value. If you have an app, if you want to write an app that would use a non-trivial database to store data for users, this talk will probably answer a lot of questions about what is Firestore, how is it better than the RTDB, the real-time database, the old solution from Firebase, how is it better than other existing database solutions, and why is it so weird? Why is it a NoSQL? Why doesn't it allow us to join data together? I think you'll have the answers to all of these questions at the end of the session. So, so without further ado, I'll get started. First, I'll talk a little bit about the background, how we came to do this, what it is for. I'll cover some best practices, and then we'll go into a more advanced land of security rules and data indexes and query data. We already talked a little bit about security rules, so probably that topic would be easy for you to follow. Querying data should also be okay. Indexing is a little bit trickier, but we won't go into too much detail there, so it should be fine. I'll also be making pauses after each topic, so that we can discuss or have questions about each of those big chunks of material. Okay. Well, many of us these days want to build apps to store data in cloud. And whether that's because we have data that we want to share among many different users, or just because we want to make sure our users can access their data from more than one device, cloud is a solution for us. But of course, we all know the pitfalls of having to, and also we know the pitfalls of having to run your own cloud, keeping the servers running 24/7, maintaining security, making sure you have enough capacity, and so on. It's not always easy to properly engineer solutions. And even though cloud solves some of the issues that you would have needed to solve before when you were storing data on your premises, you still have a lot of stuff to do still. First, you need a database server, and you've got to run and scale it yourself. Then in front of it, you need an API that lets users query the database from the apps. Now, you need to secure it, and the client will need some sync logic when you call the server and what you ask for. And finally, sometimes the client might be offline or have a spotty connection, especially if they're mobile. So you might also need to make sure your data is accessible offline. That's a lot of things to do for a simple app. And don't even get me started on what it takes to make this a real-time system. Also, what do you do if you want to target multiple platforms? Android, iOS, web. Well, get ready to rewrite your code several times. Good luck also coordinating a schema update. So that's specifically why we decided to build Cloud Firestore, our next generation database to store and synchronize app data at global scale. This is our second database in the cloud that we built as part of Firebase. We've learned a lot from our work on the real-time database over the past several years, and we incorporated many of these lessons into Firestore. We think this makes for a more compelling and powerful product. And we encourage you to look at Cloud Firestore as your primary solution for any new mobile or web application you build. Raise your hand if you tried Firestore before. Okay. Have you used RTDB before, real-time database? Okay, great. Well, for the people who didn't use any of our real-time database solutions before, let me give you a brief introduction on how it works and what makes it different from other solutions. Then we can get deeper into some pro tips and techniques. Even if you're using Cloud Firestore professionally, I think you still have a few things that you will learn. There will be a few things that you will learn today. So, Cloud Firestore. It comes with a rich client library that makes interacting with the database easy. Just like the real-time database, we support effortless syncing, with changes in your database as they happen on the client. Cloud Firestore also has a robust offline mode, so users can keep interacting with the app that includes querying data, saving changes, and so on, even when the internet isn't there or is unreachable. And if your app doesn't meet the whole real-time syncing model, you can also make a simple one-time fetch from the database. It's completely up to you. On the back end, Cloud Firestore supports a sophisticated set of security rules, which, along with Firebase authentication, can help you make sure that your users only access the data that you want them to access. Cloud Firestore is also integrated with Cloud Functions for Firebase, which allows you to run server-side code in response to changes that happen in your database or elsewhere. And all of this means you can have a truly serverless computing environment to support whatever kind of application you might want to run. And because Cloud Firestore is built on top of GCP, Google Cloud Platform, powerful infrastructure, we can provide a lot of sophisticated database features, like multi-region support, strong consistency, multi-document transactions, and the ability to scale to meet the needs of your users, no matter how popular your application becomes. So let's talk a little bit about how your data is structured in Cloud Firestore. Cloud Firestore is a document model database. All of your data is stored in documents, and the documents are stored in collections. Let's look at the document. You can think of it as something like a dictionary or a hash. It's got a set of key value pairs, which we refer to as fields. And the values for the fields can be of a bunch of different types. Anything from strings to numbers to binary values to JSON-like objects, whatever your team likes or needs. Now, these documents are stored in collections. These are, as you might expect, collections of documents. Note that documents cannot directly contain other documents, but they can point to sub-collections. And of course, the sub-collection can contain other documents, which can point to other sub-collections and so on. This structure brings with it a number of advantages. For starters, all the queries that you make are shallow. This means that you can grab a document without worrying about grabbing all the data underneath it, unlike the RTDB, the real-time database, where you would grab all the data at once. Whenever you read it, you have to read a subtree. It also means that you can structure your data hierarchically in a way that makes sense for you logically without having to worry about grabbing tons of unnecessary data. Cloud Firestore also makes it much easier to run queries that span multiple fields in a document. In many NoSQL databases, including the real-time database, this was very difficult to do. And these searches required hacks and workarounds. In Cloud Firestore, we can do this work for you, either automatically or by creating composite indexes to make these searches easy. But perhaps most important, queries in Cloud Firestore scale with the size of the result set, not the size of your database. So fetching the top 10 restaurants in Brunswick or in Bangkok with your restaurant app will take the same amount of time, no matter if you have 500 restaurants in the database or 5 million. So your app stays blazingly fast, no matter how much data you have in your collection. Now that you have a basic understanding of how Firebase data model works, let's dive into how you should choose the best data structure for your app. This is probably the most common question we get from Firestore users. And if you remember some basic rules, you should be able to answer this yourself. When working with a NoSQL document database like Cloud Firestore, you need to put a bit of thought into how you structure the data that you're used to. And it might go against your instinct from the other databases. So here's the document we showed you before. In Cloud Firestore, the document is like an atom of the system. You're regularly splitting or joining atoms. If you're doing regularly splitting or joining atoms, you're probably doing something wrong or probably trying too hard. So how do you decide where you should put the boundary for a document? For example, what about this vector field? Why not make it a sub-collection? Or could it be easier to make it a document? Here the birth document has a vector collection, and we have broken out the vector object there as a new document. After all, it's a complex object. Why shouldn't it be in its own document? Or maybe it could look like this. Having a document for each vector. What if you store everything in the top level collection and then add a birthday? Yeah? To identify the parent rather than a subcollection. Then we can just query the vector for each birth when we need them. How can you know the right approach? Well, there are a few things to consider, but the first one would be the limits of a document. After all, why not put your whole database in a single document? Then you don't have to think about structured data at all. So the first limit you need to think about is that a document can be no more than 1 megabyte. You may think this is small, but it's actually very big. For instance, the entire text of a 544-page novel, A Tale of Two Cities, is only 700 kilobytes. This is a system limit. But keeping your document small is just a generally good idea. After all, if you had 10 megabyte documents, think of how long it will take to fetch it over a 3G collection. It will be probably more than a minute. And you won't be able to split the document. Now there is a second fundamental limit. You can only have 40,000 indexes. That means you can have at most 20,000 simple fields with default indexes on them. And likely you'll hit this limit soon. You hit this limit sooner if you don't arrange the data properly. However, if you are careful on how many fields you keep in your collection, or you use a blacklisting for indexes, you'll never have to worry about this thing. I want to just point one thing. It's not the number of documents, it's not the number of collections, it's the number of indexes. And an index is formed whenever you do a query that uses a filter, or you can form indexes manually. But the indexes will only be created for a new type of query. They will not be created when you just add data to the collection. Would you like me to explain this concept a little bit into more detail before moving on? Or would you like me to cover this when we are in the index section? Okay, who wants for me to cover it now? Who wants me to cover it when we talk about indexes in detail? Okay, I'll cover it now. Okay, so why do we have this limit? So this limit is essentially a sanity check. Because whenever you add a document to a collection, we have to recompute all the indexes. Recomputing more than 40,000 indexes for every write operation is is something that's not really efficient. Now we do have those indexes so that your queries will be blazingly fast. However, that also means that whenever you write data, we'll have to make sure these indexes are consistent because Firestore is a database in which we grant consistency. Now, when do we add a new index? So whenever you write a new field to the database, if the field is a regular field, it will be added to the indexes. Also, whenever you query the data that has a filter for a specific list of fields, we'll be using the indexes for those fields. That means is, for example, you have a collection of drinks which have, let's say, a collection of cities, and the city has a name and a bunch of flags for them, and a bunch of say, list of parks. Then we'll create the index for the parks, we'll have the index for the ID and so on. However, we won't be creating new indexes just because you have a repeated list of parks. It will be a single index that will contain all of those. However, if for instance you have the geographical coordinates of each of the parks in your cities, which can be a very deep hierarchical structure, for instance you store all your geospatial geometry, that could mean hundreds of fields in your document. And that's when we can hit this kind of limit. If you have hundreds of fields inside of your JSON object, that's when you can hit this limit. So the only thing you want to be careful is whenever you have a collection that has more than a couple dozen of fields, you might want to exclude those long list of abstract fields from being indexed. If you apply this simple rule, you'll never run into this problem, ever. And you won't have to worry about this at all. I hope this was kind of clear. I just wanted to say, if you ever think if you ever think you might hit this limit, probably you're either structuring your data wrong, or you just need to blacklist a subfield in the collection, and you'll be fine. Nothing really to worry about here. And there is a third limit, which is also a bit tricky, but yet again, if you structure data correctly, you will never hit it. We have one QPS limit on sustained document writing. Of course, you can burst higher than that, but if you stay at 5 or 10 QPSs, queries per second, forever, you'll eventually fail some writes. And this is because, like I said, Firestore is always consistent. So every write will update every index. Now, the 1 QPS write limit only applies to individual documents. That means you can have a virtually unlimited number of writes in different documents and collections. But if you overwrite the same document over and over again, you'll have to be below this limit. And if you overwrite a document over and over again, you're probably doing something wrong, and you probably need to split the document in subdocuments in a collection or in a collection. Usually you would want your operation to be simple and atomic. For instance, if you have, let's take our example of city with parks. If you have a city which has a bunch of parks, and your users regularly post data about problems in those parks, for instance, whenever they spot a trash item, and you're rewriting the city object every time somebody posts a new entry there, it's probably wrong. You want to take out the data that the users are writing all the time and just put it in a separate collection. And that would allow you to have those writes being separated from the object that will be accessed by many people. And you'll never hit the limit. Okay, so now hopefully you can decide on how to split the document, what level of granularity you want to use when splitting your Firestore documents. The next question would be, would you prefer collections or sub-collections? Let's say you're making a social media app. A user has many posts in your app. Should the post be a sub-collection of the user document, or should the post be a top-level collection with just a user ID property? Does it even matter? Here's a simple example where we can show the two options and how it affects data access. So you can see that if you store things in a root-level collection, you have to use a query to get them back out. In a sub-collection, it's just a direct get operation on a path. Nowhere close. Now, in Cloud Firestore, these two operations are at the same speed. So there is no performance difference. It's most about how you organize data. In the first case, you have all the user posts sort of lumped together, and you have to add a property to distinguish in between those. In the second example, you know where all the user posts are without any extra properties. So here's a case where there is a difference. Let's do the same fetch as the last time, but add an order by clause so that we get the posts back from newest to oldest. Well, in this case, a root level collection, you need to add a component index in order to do this query. Since your query has both a where and an order by, you need an index on the user ID and the type. In the second case, you're only doing a single clause query, so there is no where. So the built-in indexes can handle this query for you. In this way, you can think of sub-collection as giving you a free, invisible where query in each collection. So essentially, if you remember the talk about indexes, the only difference is that in the first case, we have this component index that is required because we have two fields that we use in our query. So this one would be a simpler solution if you only access posts that belong to a single user in your basic use cases. Yeah. Now let's say you wanted to get all posts in the whole database with more than 5 votes to make a leaderboard. Well, if you have your posts in the root level collections, it's very simple. If you have your posts in the sub collection, you're out of time. You can't query across parents. The data is not indexed in that way. Now, if we do want to bring this collection group type of query we do want to bring this type of collection to Cloud Firestore in the future. But for now, the limit is something you need to keep in mind when structuring data. So if you think you need this type of query, for now, you'll have to bundle your documents together in a single collection. That shouldn't stop you from splitting the data. If for instance, you know that you won't need this kind of functionality for now, and you might need it later, that should be fine. You can use cloud functions to do some data updating whenever something changes. So that shouldn't stop you to use the separate collection if you think you don't need this right now, even if you're worried that you might need it in a year or two. However, if you know that you will need it soon, it's best to split the data this way, to not split the data initially. Okay, these are the things we have to remember when organizing our data. Documents have fundamental limits that we cannot exceed. Collections and sub-collections have different strengths and weaknesses. And try to think ahead of how you want to use your data and then store it that way. Work backwards from your queries that you want to do to the data structure. And that will enable you to have an easily to maintain collection and generally save a bunch of time when writing your application. Okay, that was the end of the first part. Now we have 3 advanced topics about how queries work, how indexes work, and how security rules should be set up. Let's make a short pause here. If you have any questions, I'll be happy to answer them. And then I'll try to just briefly introduce the topic that might be of most interest to you, instead of going into my detail for stuff that you probably won't be using right away. Okay. So are there any questions at this moment?
มีคำถามไหมครับผม Any question?
Okay, cool. I'll talk a little bit of how querying works, so that you will know which kind of queries are permitted, which are not permitted, and which queries, and how we can assure the queries are super fast. Okay, like I said, we don't allow queries. But how is this possible? I'm going to skip a little bit ahead and explain why we have, how it's possible to have all the queries fast, no matter how many documents you have, and no matter how many filters you have on those queries. The reason why our queries are super blazingly fast, and the reason why our database can scale horizontally, no matter how much data is because we use the concept of zigzag merge joins. What that means is, whenever you write a query that uses more than one index, we'll do this kind of zigzag jumping in between the indexes, so that each lookup will take almost a constant amount of time. The way it works is you'll find the first document that corresponds to one of your filters in one of the indexes. We'll then jump to the second index. And because all of the indexes have a secondary ordering by document ID, as soon as we find the first entry, we have the guarantee that we can use this order to look up the next document. So we'll advance through all the indexes horizontally until we find the first matching document. Then we'll advance to the next entry in one of our indexes and jump back to the previous index. Find the next document that matches that index as well, and so on. So we'll essentially be zigzagging through all our indexes with close to constant speed. This way, the speed of lookup will be essentially proportional to the number of the results you'll be getting, and will be minimally affected by the amount of documents in your database. Because of this, we also have a restriction, and I'll quickly show what the restriction is. We cannot do a query like this. Because of the fact that we use a zigzag indexing, we cannot have a where clause that is not an equality for more than two distinct fields. We can, of course, have one comparison where clause. We can have a sorting clause. We can have a virtually unlimited number of equality clause, but we are restricted to only one comparison filter. That's the one restriction you have to keep in mind when designing your databases. When you write your queries, you are restricted to only one field in a where filter that has a more or less operation in it. So if you remember one thing from the way our queries work, is this: you'll have to structure your data in such a way that that you can query the data without having to use more than one comparison filter. That's the first advanced topic. Now let's do the second advanced topic, security. I've already covered a bunch of security best practices, so I'll just jump to the things that's specific to the database. Okay. There is one thing I want you to remember. All the security rules in Firebase will be merged using an OR operation. This means that even if your first rule denies access to data, if you have a secondary rule that allows it, the operation will be allowed. So that's why it's very important to be sure to keep the rules as granular and as isolated as possible. You don't want to have a superset rule that would allow essentially for you to do any kind of read or write to a sub-collection, to a collection, because you can easily forget about it. And that's why it's also really cool to use the rule simulator, because the rule simulator will show you that the first rule actually was true, even though you think that you limited access based on the second rule. So one thing to remember here is the rules are always applied with the NOR operation. And if you need AND operations, you just have to cover a longer rule. That's where the functions come in. They can simplify, they can make the code more readable so that you don't have a really long rule for your data. Now there is another thing which I also covered in the security section, is that rules are not filters. So when you write rules, you want to be careful that you're restricting access based on guarantees, not on the actual data in the database. If for instance, you're getting a read access, a read query. So if you have a rule that restricts access to a specific group of documents in a collection, you have to make sure you also reflect this rule in your query. Else, it will always fail. Just remember the second thing. It will save you a lot of time debugging if you just remember these two concepts. And this is about security. By the way, all the queries are denied by default. So if you remove all the rules, all your queries will be denied. And this is by default. And maybe the third one, I didn't cover this one. Rules don't cascade, which you'll actually figure out on your own. As soon as you have a sub-collection and you allow an operation to the parent collection, you'll see that the sub-collection doesn't actually allow you to do anything by default. This is also by design. The rules only apply to the collection they're specifically written for. They will not apply to child collection. And this is the second advanced topic. And yeah, I think that's it. That's it. We also know that developers don't always have control over the stack that they use. So integrating with legacy systems is a must. That's why we publish the REST API for most of our products, including Firestore. So that whether you're using an environment in which Firebase is fully supported as an SDK, or you have a more exotic or legacy system which you still want to use, then there's multiple ways for you to approach that integrations. Either by using our RESTful APIs or by using the cloud functions to describe your logic. There's always at least one way to get your data to and from database in a meaningful way. Should you have any additional questions, feel free to find me later and I'll be happy to address them. Thank you for being here today. You can follow me or message me on Twitter, and I can't wait to hear about the amazing product that you'll build using Firebase. Thank you.